Hi, today we'll be going over a model that performs weed detection using an object detection neural network. According to a 2019 study, about one-third of yield goes unharvested. That's a significant opportunity to reduce waste and increase profits. On average, the size of a US farm is about 400 acres. Farmer Sam is a wheat farm and wants to make the most of this opportunity. He's divided his field into three parts. How can he decide where to farm? One way is to look at images from fields and determine which field has the best harvest. He's decided to count the number of wheat heads in each image and harvest in the field with the most wheat heads and the wheat heads of the best quality. However, counting wheat heads in each image and gauging their size can be cumbersome. Can you count how many there are in each image? So farmer Sam decided to build an object detection neural network to make his life easier and bound the wheat heads for him. By bounding the wheat heads, he can gauge the quality of the yield on each field and the quantity. To do the job, farmer Sam gathered and cleaned the data. Then he built an EfficientDet model, a relatively new and well-performing object detection model. And lastly,
The main dataset Farmer Sam chose to work with is the GWHD, or Global Wheathead Detection dataset. This dataset contains many different images from wheat varieties from around the world, such as Swiss, French, and Japanese wheat plants. As you can tell, each image is annotated with bounding boxes, which are tuples denoting the x and y coordinates of the top left corner of the box, as well as the height and width of the box. Each box denotes a wheat head. As mentioned, these wheat varieties are from around the world. To test if his models are capable of understanding what a wheat plant truly looks like as opposed to learning specific species, Farmer Sam split his dataset into training and validation and testing datasets by geography. To further augment the dataset, Farmer Sam generated 500 new images by applying transformations to existing images. For example, he rotated the image of a French wheat plant by 180 degrees. In total, he applied 5 transformations, 90, 180, and 270 degree rotations, and reflections about the x and y axis. To round out his dataset, Farmer Sam introduced hand-annotated images from the ACID, or Annotated Crop Image Database dataset. These are images of wheat plants in entirely different contexts. Testing on these images will enable Farmer Sam to learn if his models are truly capable of understanding what wheat heads look like, rather than just learning what overhead shots of wheat heads look like. In total, the final dataset used has 3,774 training and validation images, 1,458 testing images, and over 200,000 bounding boxes.
The architecture that Farmer Sam uses is EfficientDet, which, as seen in this plot, has high accuracy while requiring few floating point operations, which ultimately leads to less time for inference. EfficientDet contains 4 layers: the backbone layer, BFPN layer, BoxNet, and ClassNet. Backbone is where the model uses the convolutional layers of EfficientNet to extract important abstract features from the image. In this process, it reduces the resolution of the image to a low-resolution feature vector. BFPN then reconstructs the high-resolution image from the feature vector of the backbone, so that each resolution, or level, the reconstructed image contains important feature information. It also mixes the information between the levels. At this point, you may think, why does SAM need multiple levels? Well, think about the problem. In an image, there are large wheat heads as well as small wheat heads. We want to be able to detect large wheat head in a low-resolution image, and we need to go to a high-resolution image to be able to see the smaller wheat heads. After the first 2 layers, we are done with feature extraction. Then, to understand the prediction of the model, we need to understand BoxNet and ClassNet, from which we need to understand anchors.
Anchors are boxes that represent the model's prior belief of the shape and the location of the object on the image. To detect the object, the model casts a set of prior predictions to move anchors evenly across the image. In reality, SAM has up to 20,000 anchors, but for now we can simplify it to 9 anchors as seen in this image. BoxNet and ClassNet looks at each of these anchors and perform predictions. As seen, ClassNet predicts the label of each anchor, whilst BoxNet detects the relative offset of each anchor. When combined together, this is what the prediction looks like.
One thing to note, since the offset of the background anchor is irrelevant, it is not shown here.
To evaluate the performance of his models, Sam calculated the intersection over union of the predicted and ground truth bounding boxes. Boxes with IOU greater than or equal to 0.5 are true positive boxes. Those smaller than 0.5 are false positive, and missing boxes are false negative. For each image, Sam calculated the precision and recall. The higher those values, the better the model. He picked 15 images from the test set and counted the number of true positive, and false negative boxes predicted by FastRCNN. It seemed that there was a problem with one of those images. Sam visualized two images using green ground truth boxes and red predicted boxes, and found that FastStar CNN failed to detect a large number of wheatheads on this blurry image. He decided to see if EfficientDet is able to make a better prediction on that blurry image. While training EfficientDet, the bounding boxes became more accurate as the number of epochs increased. As a result, EfficientDet did perform better on that blurry image compared with FastStar CNN. But what about its performance on the whole dataset? Sam calculated the precision and recall of EfficientDet and two baseline models on a test set of 500 images, and found that EfficientDet with trained weights did have a better performance compared with faster RCNN. There is one problem though. Images in the trained, validation, and test set are all aerial pictures of wheatheads. To find out if the model really knows how to recognize wheatheads, Sam decided to test EfficientDet on a completely new dataset, the ACID database, which has images taken from a completely different angle. After testing on ACID, Sam compared the results of FastRCNN and EfficientDet again. Taking two sets of bounding boxes as an example, he found that EfficientDet still has some problems with detecting covered wheatheads, but the results are still generally better.